Imagine a hunger so subtle you don't feel it. Your stomach isn't growling. You don't feel weak, at least not yet. But deep inside your body, a critical countdown has begun. This is the story of hidden hunger, a crisis affecting millions of people worldwide, where the lack of a single microscopic molecule can lead to blindness, immune collapse, and death. For decades, scientists have faced a deadly paradox. We know we need this molecule, vitamin A, to survive, but we also know that having too much of it can be toxic, even fatal. And the only accurate way to measure how much you actually have inside you? Until recently, it required sticking a needle into your liver. But here's the part most people don't realize. Researchers have found a way to bypass the needle. They are using a technique that sounds like science fiction, swapping atoms in your food to turn them into microscopic spies. This is the story of a clinical trial, a groundbreaking experiment spanning 2 continents designed to rewrite the rulebook on human survival. It's a tale of Indonesian villages, American laboratories, and the quest to find the perfect biological balance before time runs out. To understand why this specific trial is so important, we first have to understand the molecule at the center of it, vitamin A. You might know it as the thing in carrots that helps you see in the dark, and that is true. Vitamin A is the essential component of rhodopsin, the protein in your eyes that absorbs light. Without it, you are literally blind in low light. But vision is just the tip of the iceberg. Vitamin A is what biologists call a morphogen. It doesn't just sit there. It dictates the shape and destiny of your cells. It tells your immune system which cells to attack and which to leave alone. It maintains the barrier of your skin and your gut. In children, a lack of vitamin A is catastrophic. It is the leading cause of preventable childhood blindness globally. Even more terrifying, a child with vitamin A deficiency has a significantly higher risk of dying from common infections like measles or diarrhea because their internal barriers, the walls of the fortress, have crumbled. So the solution seems simple, right? Just give everyone vitamin A supplements, flood the system, fix the problem. But this is where things get complicated. Unlike vitamin C, which is water-soluble and easily flushed out of your body if you take too much, vitamin A is fat-soluble.
Your body doesn't throw it away. It hoards it. It stores it in the liver, treating it like gold bullion in a vault. If that vault gets too full, the gold turns into poison. Hypervitaminosis A, vitamin toxicity, can cause liver damage, bone pain, skin peeling, and increased pressure in the brain. In pregnant women, high doses can cause severe birth defects. This creates a massive global health dilemma. In wealthy nations like the United States, people get vitamin A from fortified milk, cereals, and a diverse diet. They might be at risk of having too much. In developing nations like parts of Indonesia, diets often rely on rice, which has 0 vitamin A, leading to widespread deficiency. Here is the scientific roadblock that has plagued researchers for 50 years. How do we know how much is just right? The standard blood test, checking serum retinol, is notoriously unreliable. Why? Because the liver is a master regulator. It keeps the amount of vitamin A in your blood strictly controlled. Your liver could be 99% empty, dangerously close to deficiency, or 99% full, dangerously close to toxicity, and your blood test would look exactly the same. The blood levels only drop when the liver is completely empty, by which time it's often too late. Historically, the only way to know the truth was a liver biopsy. A doctor would have to insert a long needle through the abdomen and extract a piece of liver tissue to analyze it. You cannot do this ethically in healthy children or pregnant women just to check their vitamin levels. It's too invasive. It's too dangerous. So for decades, the recommended dietary allowances, the RDA numbers you see on nutrition labels, have been based on estimates, animal studies, and educated guesses. We haven't had a precise fuel gauge for the human body. Until now. What researchers are studying? This brings us to this trial. The researchers, led by experts in nutritional science, are not testing a new drug. They are testing a new way to see inside the human body without cutting it open. They are using a method called Retinol Isotope Dilution, or RID. This is where the science gets incredibly cool. Imagine you have a swimming pool, and you want to know exactly how many gallons of water are in it, but you can't drain it, and you can't measure the dimensions because it's an irregular shape. How do you find the volume? Here is the trick. You take a small cup of red food dye.
You know exactly how many molecules of dye are in that cup. You pour it into the pool and wait for it to mix completely. Then, you take a cup of water out of the pool. By measuring how diluted the red dye is, how faint the pink color has become, you can mathematically calculate the exact volume of the entire pool. If the dye is very concentrated, the pool is small. If the dye is incredibly faint, the pool is huge. This study is applying this pool and dye logic to the human liver, but instead of red dye, which would be useless, they are using heavy vitamin A. In nature, atoms like carbon usually have a specific weight, carbon-12, but there are stable isotopes, versions of carbon that have an extra neutron, carbon-13. They aren't radioactive, they are just slightly heavier. Researchers created synthetic vitamin A molecules where the normal carbon atoms were swapped for carbon-13. When a participant swallows this heavy vitamin, their body treats it exactly like normal vitamin A. It absorbs it, transports it, and stores it in liver. It mixes with the pool of natural vitamin A already there. After a few weeks, the researchers draw a small sample of blood. They use a mass spectrometer, a highly sensitive scale for molecules, to weigh the vitamin A in the blood. They look at the ratio. How much is the heavy version versus the normal version? From this single ratio, they can calculate the total amount of vitamin A stored in the participant's liver. They have created a virtual window into the organ. But the trial didn't stop at just measuring. They wanted to see how the body uses this vitamin over time. They wanted to determine the exact burn rate of vitamin A in women of reproductive age. This is the holy grail of nutrition science, knowing exactly how many micrograms you need to eat every day to replace what you lose, ensuring you stay in the safe zone, neither deficient nor toxic. How the trial works. Let's walk through the actual methodology of this study. This was a sophisticated cross-continental study designed to capture the extremes of the human experience with vitamin A. The researchers recruited two distinct groups of women. Group 1 was in the United States. These women likely had high vitamin A stores. They eat dairy, fortified cereals, and meat. Their livers were expected to be well-stocked, perhaps even overstocked. Group 2 was in Indonesia. These women were selected because they were likely to have lower vitamin A stores. Their diet is traditionally rice-based, and while initiatives to combat deficiency exist, the baseline is often much lower than in the West. Why compare these two groups? Because the body is smart. It might use vitamin A differently when it's scarce versus when it's abundant. If you have a full bank account, you might spend money freely. If you are broke, you pinch every penny. The researchers hypothesized the liver might do the same with vitamin A, conserving it when stores are low and burning it off when stores are high. The trial design was elegant in its rigorous simplicity. First, all participants underwent the baseline RID. They drank a precise dose of the heavy carbon-labeled vitamin A. Then there was a waiting period. This is crucial. You have to let the dye mix with the pool. The vitamin A has to travel from the stomach to the blood to the liver, be processed by specialized cells called stellate cells, and then be released back into the blood. This equilibration takes time, usually about 2 weeks. After the waiting period, blood was drawn. The mass spectrometer gave the baseline reading. Here is exactly how much vitamin A is in your liver right now. Then came the intervention phase. For the next roughly 2 months, 42 days in the USA, 60 days in Indonesia, the women were assigned to different daily treatments. Some received a placebo, oil with no vitamin A. This allowed researchers to see how fast the liver stores dropped naturally when no new vitamin was coming in. Others received specific doses of vitamin A, 175 micrograms or 525 micrograms. These numbers weren't chosen at random. They represent different fractions of the RDA. 525 micrograms is close to the estimated requirement. By feeding them a known amount every day, the researchers controlled the input into the system. At the end of the 2 months, they performed another RID test. They gave a second dose of heavy vitamin A, labeled differently, perhaps with deuterium, to distinguish it from the first dose, and measured the liver stores again. Here is the mathematical magic. They knew the starting liver store, they knew exactly how much vitamin A the women ate during the trial, and they knew the ending liver store. Starting store plus what was eaten minus what was burned equals what was ending store. Since they knew 3 of those variables, they could solve for the missing one, what was burned. They could calculate with unprecedented precision the daily utilization rate of vitamin A in the human body. They could see if the American women spent their vitamin A faster than the Indonesian women. They could see if the women on the placebo diet conserved their stores efficiently or if they continued to lose them. This kind of data is exceptionally rare. Most nutrition advice is based on what people say they ate, which is often wrong, and how they feel, which is subjective. This trial used atomic physics to track the movement of nutrients molecule by molecule. What could this mean? The implications of this study are profound, extending far beyond a simple vitamin supplement. First, let's look at the global safety net. The World Health Organization, WHO, and governments use RDA values to decide on food fortification. In the US, milk is fortified. In other countries, sugar or cooking oil might be fortified. If the RDA is set too high because we overestimate how much the body burns, we risk slowly poisoning populations with chronic hypervitaminosis. We are already seeing signs of this in the West. Osteoporosis and bone fractures in the elderly have been linked to high vitamin A intake over a lifetime. If this trial shows that our bodies are more efficient at conserving vitamin A than we thought, it could lead to a lowering of the RDA. We might be telling people to take too much. Conversely, for the developing world, this data is a lifeline. If we know exactly how much vitamin A is needed to maintain a safe liver reserve, aid organizations can design better interventions. Instead of high-dose mega supplements that spike blood levels but might not be stored efficiently, we might find that smaller, steady doses are far more effective at building the bank account in the liver. But here's the part that really excites scientists: the validation of the tool. By proving that the RID method matches up with the expected biological math, this trial validates the heavy water method for wider use. Imagine a world where we don't need to guess if a population is malnourished. We could go into a village, give a sample group a drink of labeled water/vitamin, come back in 2 weeks for a finger prick blood test, and know exactly the nutritional status of that community. No guesswork, no invasive surgery. Furthermore, this trial sheds light on the superperson concept in nutrition modeling. Sherry Tanumi Harjo and her colleagues have pioneered the use of mathematical models that treat the human body's compartments, blood, liver, kidneys, as a complex system of equations. This trial provides the hard data to tune those equations. It moves nutrition from an observational art to a computational science. Now, you might be wondering about the safety of drinking heavy isotopes. Is it radioactive? Is it dangerous? This is a common misconception. The isotopes used, carbon-13 and deuterium, are stable. They do not decay, they do not emit radiation. They are already inside you. About 1% of the carbon atoms in your body right now are carbon-13. The trial simply increases that percentage slightly in the vitamin A molecules. It is completely harmless and indistinguishable from nature, except to a mass spectrometer. The ethical considerations of this trial were significant. In Indonesia, where deficiency is a risk, giving a placebo, no vitamin A, for 60 days had to be carefully weighed. The researchers ensured that the duration was short enough that no participant would drop into dangerous deficiency levels. They monitored the women closely, and crucially, at the end of the trial, participants likely received support or supplementation to ensure they were left in better health than when they started. This highlights the slow, careful nature of clinical research. You cannot just experiment on people. Every step, every dose, every blood draw was scrutinized by review boards in both the US and Indonesia to ensure that the quest for knowledge never compromised the safety of the women volunteering their bodies for science. So, what is the takeaway from this study? It is a reminder that the most important battles in health are often fought on the microscopic level. We used to think of nutrition as just eating food. Now we understand it as a complex dance of chemistry, storage, and utilization. This trial represents a shift in how we understand our own bodies. We are moving away from guessing and towards measuring. By using the clever physics of stable isotopes, we can peer into the black box of the liver and read the fuel gauge of human life. The data from this study will likely ripple out into policy changes, textbook updates, and international aid strategies for decades.
It will help ensure that a child in Indonesia gets enough vitamin A to see the stars,
while a retiree in America doesn't get so much that their bones become brittle. It is the search for the perfect balance. Science is a process of refinement. We start with a guess, we move to an estimate, and finally, through trials like this one, we arrive at the truth. Disclaimer: this video is for educational purposes only and does not constitute medical advice. Vitamin A toxicity and deficiency are serious medical conditions. Always consult a healthcare professional before making changes to your diet or supplement routine. If you enjoyed this deep dive into the hidden science of nutrition, keep asking questions and stay curious.